Today we are going to do section 2.2. So first let me scan in the book. Let's see, this is page 66 and 67. Okay. And then next, page 68 and 69. Let me see. Let's zoom in a little bit. Okay. And then zoom in a little bit on top. And the bottom. Okay. And finally, the homework page, the last of the homework page, 70 and 71. All right, let's see. Here it is. Okay, and then zoom in a little closer on top and, oops, and on the bottom. This thing is tilted there. All right, that should do it. So in section 2.2, we're going to review quite a bit of the vector stuff we learned in Calculus 3, but also introduce certain new ideas and specifically problems to do. Okay, so I want to quickly review what we learned in Calculus 3 in relation to this matter. And just to refresh your memory, all right. First, the plane. What is the plane? The plane is some normal vector the plane is n dot pq, where pq is some line, I guess. PQ is something. I'm not even going to explain what it is. I just want to refresh you real quick. If you want to look this up a little more, it is in the book Calculus 3 on page 195. I have the book for download. So in the video description. So anyway, so there's this stuff. I want you to look at it quickly. Remember, plane has something to do with n dot pq, right? Which translates into this equation, which we don't care right now, but just want you to see that. And then we have also learned how to write the equation of a plane given 3 points, given a point and a line, and the distance between a plane and a point. Okay, we learned that at some point. Yeah. Anyway, so let's move on. And the line of section of two planes, angle between two planes, and distance from a point to a plane. We will be doing that today, okay? But that was done before, as you notice. And finally, distance between parallel planes. We didn't really do that. I just wrote all that down just to remind you that you did that at one point when you studied Calculus 3. You probably don't remember all that stuff right now, right? But that's okay, okay? Don't remember the details of all that stuff. I just want you to remember vaguely that you did that at one point. And this is the center of mass formula, which we will need at one point for problem 5. Just take a quick look at it. That's also covered in Calculus 3 or in physics, or you just look this formula up, okay? We just need that formula. Cross product is, what's the cross product? Remember, the cross product also is defined as, going to be perpendicular to the product is crossing, right? A cross B is perpendicular to both A and B. And of course, A cross B, the magnitude of, they didn't write the magnitude here. Well, whatever. It equals the AB sine theta. And so the next thing I need to remind you is actually from trigonometry. I just wrote this down. Oh no, this is very hard to see. But I guess it looks okay. So it's the law of cosines and the law of sines. Okay, remember what they are. We'll need it in one of the problems. And finally, what is the directional cosines? This was mentioned in the previous section, and I forgot to talk about it quickly. The directional cosines are if you're given a vector, the directional cosines is the cosines of the angles the vector make with each major axis. See, alpha, beta, gamma, and it makes certain angle, and if we calculate the cosines, then it gives you the direction of the vector, basically. And specifically, it has a certain relationship as well. The book also defined it that way. Okay, is component. That is the directional cosines is calculated by each component of the vector. Where's my AIBJ? Where's I'm missing the last CK in my vector. I didn't see that. Whatever. Well, the point is that. That's the directional cosines. You have, and also I should mention that all the directional cosines is down here. They all add up to be 1 because of how they're defined. Okay, if you add them, if you score them and add them up, you can see very quickly why they should be 1. But that's the meaning of the directional cosine. It is the cosine of the angles that the vector make with each axis. All right, so with that, we should be good to start. Let's see. Okay, let's start on page 66. Now, being that this is a review of some of the stuff I mentioned and some of the stuff I haven't mentioned yet, doesn't matter, on page 66, please read this stuff carefully, okay? Starting on off page 66, I'm talking about this part where everything is defined from the beginning, but it's not that complete. Okay, the book mentions a lot of the stuff, but not all the stuff. But it's important to review these. But not all the stuff. But not all the stuff is actually. But not all the not all the stuff is actually old. Some of the stuff is new. So please read page 66, and on page 67, the first item, the angle between two vectors is given by the dot product. That's one way you can calculate it. Is the dot cosine theta is r dot s over r magnitude of r and s. That is from the past, but we will prove that in a little bit. Okay, and then moving, if you read moving on, everything looks like familiar until you get to item I. And the condition I, where RST are parallel to a plane, means RST equal to 0. Now that probably doesn't sound familiar, that's because it's not. This is a new concept, and we're going to prove it in the homework. Okay, so but notice that when it says RST are parallel to a plane, that doesn't mean RST are parallel to each other. They can form a triangle. Okay, and in fact, they don't even have to form a triangle. They can be skewed lines in because we're talking about 3 dimensions, so they can be just 3 skewed lines in different parts of space. They just all happen to be parallel to a plane. Because being parallel to a plane means you can be anywhere, right? And let's see, like say if this thing is a plane and my pen is the line, right? It can be here, as long as parallel. See, this is parallel, so is this. As long as parallel, I mean, it can be anywhere, really. Out in on the other side. So the 3 lines that are parallel to the plane can really be anywhere in space, because that's so please do not limit yourself to thinking the 3 lines on the same plane, because now we're thinking in space. So things move around a lot in space. There's a lot of space to move around in. Anyway, so please continue reading. Okay, all the rest of the stuff is I think most of it is fairly either is from the past, directly as a theorem, or we calculated it at one point. But some of them we will still talk about it, like item L. I think we'll also prove that in the homework, and item N as well. So please read the rest of the items. Okay, they are I'm not going to reprove them here because we already did that in the past, and really all you should do is just refresh your memory of this fact being true. And that's good enough. Okay, it's not necessary to reprove any one of them because we did that at one point. Okay, now so looking down at subsection 2.2, where we have, there's the mention of directional cosines again, but we have, as I've explained, they're just the cosines of the angles that the vector make with each major axis. And then, so next let's prove formula E, okay? Formula E is now going to be, I don't remember how it was proved before, but now we're going to prove it by the law of cosines. That might have been how it was proved before anyway. Okay, so if you look at that, to prove it by the law of cosines, what we're going to do is use the dot product. Okay, there's a law of cosines has a bunch of squares, right? Which says law of cosines basically says c squared equals a squared plus b squared minus 2ab cosine c. Right? So then the squared, we are going to represent the squared as a dot product by itself. For example, the first one, from the origin to r squared, will represent it as the vector r dot itself. And that is a recurring theme that this is a trick that you must remember for this section. That is, when you calculate something squared, how are we going to do it? We're doing vector algebra now. So you always you represent the square. The first thing you think of is the product dot itself. Okay, then you turn it back into a vector manipulation. So then it equals to r dot r. Okay, the other squared becomes s dot s, and then we continue doing that. And then especially the magnitude squared is this thing dot itself. This is r minus s dot r minus s, and which comes up with this because the dot product works pretty nicely just like regular multiplication. And then so by the time we're done with that, then eventually you realize this is exactly equation E. Once you cancel out some redundant parts and then isolate the cosine, it all comes out nicely. So please do this yourself, okay? If the book does it, then we'll do it. Is my idea. If the book doesn't bother repeating the proof, then we're not going to bother either. Okay, we'll just go right along. And so the next thing we need to do is, and let me see. Now, continuing on page 68, let's look at equation G, I guess. We have, equation G on the previous page states that if the two vectors are parallel, then one is a constant multiple of the other. Well, assuming they're not both 0 and stuff like that. And so any of them 0 or something. Anyway, so that one is the multiple of another. We did this in a previous homework problem, okay? And so the next thing is that when they are parallel also means that the cross product is 0. Now to see that, we have a comment and when we do the cross product, as you can see, when r is crossing s, okay? And we can pull the constant out because that's one of the rules. So that makes it more convenient. And then once you have something crossing itself, that equals to 0. And on the other hand, if the cross product is 0, then the square of the magnitude of the cross product, okay, we will which will be equal to 0 again, right? Because being there is a zero vector, and that would be equal to, using the Lagrange theorem identity on page 64, we get this thing, okay? And your book has a small mistake of adding squares here, too many squares. There's no need for the squares here, because if you confirm this equation with a Lagrange identity, then you get that thing, really. It's just, is r cross s, because the magnitude, okay, is r cross s dot r cross s, right? Which is what, well, that's a different problem, but we're doing the same thing. So we're doing r cross s dot r cross s, which is this one, which by Lagrange's identity equals to this, is first thing dot the first and second dot second, that sort of thing. Okay, so if you can please confirm this. And so there is no squared in there. And as a result of that, by the time, let me see, by the time you get through that, then that would mean from this equation, then you can set the two sides of that equation as equal, then then r dot r, and so then r dot s, take the square root, will be equal to the magnitude of r and s. All right. So then plus or minus, of course, because this thing is this chunk r dot r s dot s is this thing squared. Okay, because that's r squared times x squared. So then it becomes this, the absolute value, I mean. So so that's how we got to this thing. And as a result of that, and then if we look at formula E in the previous page, where cosine is the dot divided by that chunk, okay? And remember cosine theta. Then coming back, then we notice that that means the cosine theta being 1 divided by another, cosine theta then being this one divided by that one, it will be equal to plus or minus 1, which means the angle would be the cosine theta plus or minus 1. That means the angle is 0 or 180, which means the two vectors are then parallel to each other. And then, of course, we assume that nothing is a zero vector, because then it's not much worth repeating. Now, let's move on to the next part, where we're considering r cross s is perpendicular to both r and s. Now, to show perpendicular, what we're going to do is, let me see. Well, I don't know what I was seeing. Anyway, so the perpendicular business is come from r cross s. We'll dot. Let's check to see if they're perpendicular by taking the dot product. And you notice that if we do the dot product by this is the definition, one of the things from page 64 again, okay, where the determinant equals to, you can write it that way, okay, check page 64. And then remember, one of the determinant rules is that if you have two rows or columns that are repeating itself, then the determinant is automatically 0, which is why this is 0 and so is that. And if the dot product is 0, that means the two things are now give me a second. I want to show you the determinant thing. Right, if the dot product is 0, that means the two things are perpendicular. And remember this rule from the determinant, okay, rule 3, which says that if one row is multiple of another row, especially if it's a multiple of 1, that is they're the same, then the determinant will be 0. Okay, that is one of the old rules. And so as a result, the r cross s is then perpendicular to both r and s. Now the next, what about s cross r? Being the s cross r will dot it and also be 0, because s cross r is just the negative of r cross s. So one's 0, the other one's going to be 0 as well, because you're just slapping on the negative sign. So then the vectors, the next sentence is interesting. Okay, the book says that the vectors r cross s have the same disposition. Okay, now look how cute the word they use. The same disposition as the major axis, okay, the XYZ axis. And so what does that mean? That just means that the vectors rs and r cross s follow the right-hand rule. That is, when you put your fingers along r, okay, swing it to s, and your thumb points to where r cross s is going to be. And then it's the same way as the ijk of the major axis. Now and also if we notice that if we do rs r cross s, that will be end up being the magnitude squared, which is bigger than 0. Okay. Whereas if you flip it around, then it suddenly becomes a negative value. Because that's how the dot and cross product works out. So then the sign, as a result, the sign of the determinant will show the so-called disposition. That is, whether it's following the right-hand rule or not. Okay, there's only two options. Either it follows the right-hand rule or it doesn't. So the positive shows it's following the right-hand rule, and the negative shows that it is not. So now we have, the next thing we have by E, that E is that cosine thing, Okay, E says condition E says that or whatever. E says that cosine theta is R dot S over magnitude of R times S. And if that is the case, then you can have an equation of R dot S, and that gives us what give us what R dot S means. Now R dot S is what that end up meaning is the product of the length of one vector by the length of the projection of the other one on it. So then if they're not parallel, well, anyway, so that is the meaning of R dot S, which we're good. Now we'll look for the meaning of our cross S. That is, what is the magnitude of this thing? That, as we already know from the past, our cross S is the area of the two vectors of the parallelogram formed by the two vectors. But we're going to prove that here again. Okay. Now our cross S is perpendicular to R and S, but what is its length? Its length is the area of the parallelogram, okay, with our S being the adjacent sides. And the way we prove it is from the area, if we do it geometrically, would be RS sine theta, okay? And if you draw up the parallelogram. And so from there, we'll substitute the sine theta with the square root of 1 minus cosine squared theta, the Pythagoras theorem for trigonometry, and then we'll plug something in to look like let's see, look like this. We have we'll plug in and do some math, okay? So we have our S is square root of cosine theta, and then that. Remember, cosine theta is this thing, okay, by condition E. And so then we plug it in and do some algebra, and it'll come out, and the RS outside will cancel out with the RS under the square root sign. And the next thing you know, we have just R cross S if you apply this thing, which is the Lagrange identity, okay, which goes back to being the cross product. And yeah, and I don't know if I mentioned this before, but that is equal to that, okay, if you, well, just check the Lagrange identity, and the same thing here. So that is how this end up being R cross S. Now please do this yourself, okay? And read the rest of this page, three more lines here carefully. The entire page, and most of it is review of past knowledge, but please read each sentence carefully and to see what the author wants point out, various interesting points that in the past we might have not have mentioned, or we might have mentioned it but didn't really pay much attention. So it's a really good refreshment of, well, refreshing our memory and also understanding of how vectors work. And so next, let's look at the following page, okay? Page 69, where we have two examples. Page 69. And the two examples then, let's look at example A. All right. Now, example A, we have, so let's first look at example A. Now, if you have n vectors that are joined end to end, then you will form some kind of a polygon, right? N polygon all the way to the end. So then eventually, then their sum of these vectors will become 0. Now, to demonstrate this, we will consider it when n equals to 5, so that we have a bunch of vectors A, B, C, D, E. Okay, go all the way closed. Then the 5 vectors form the side, and we can do the subtraction. Now this skill is important for doing homework. Okay, let's so each vector then, each point has a name to it. This is vector A and B, and you keep going. Okay, and eventually C, D, E. But each section has is called, for example, this is called B minus A. Okay, and the next one is called C minus B, because the vector is given as let's see, what by condition B, that the rule B, let's say in the previous page, the vector is given as the n subtracted by the final subtracted by the beginning. Okay, so then as you can see, if you have b minus a, if you add them all up, that will become the it will get to the end eventually. So then when you add them all up, then eventually each thing will subtract itself out in the next step, and then eventually you get 0 out of it. Now, so the sum will become 0. Now, the last sentence in this example is interesting. It says, note the polygon is not necessarily plane nor convex. And so it's not like a polygon we normally think of. If we're talking about a polygon in space, and the word polygon is only used because it's a closed shape with 5 sides. So I drew one on the Desmos 3D calculator to show you. Okay, here is a polygon. I have it shown in three different angles, okay, 3 random angles, and as you can see, that doesn't even look like the same polygon, but I assure you it is, okay. If you're interested, please plot this yourself. You don't have to, it's just a point of interesting, or you can just trust me that this odd looking thing from all 3 directions actually is the same object, okay. And I just found some random points from -5 to 5 and plotted this thing out this way just for a point of interest. And where did I get the numbers, you say? I used the random number generator. Okay, so I suggest you do the same if you're interested in using the Desmos 3D, which I think is quite cute. So, but you notice that, yeah, a polygon in space can really be messed up, okay? It doesn't even look like anything. So that's that. And the next thing I want to we'll talk about is, oh man, I knew that was going to happen. Well, anyway, the next thing we'll talk about is the next example where we are going to prove the Pythagoras theorem. Isn't that exciting? Yeah. Anyway, to prove the Pythagoras theorem, okay, we're going to take 3 vectors R, S, T and form a triangle, right angle triangle out of it, okay, and S and T being the legs. Now, that's fine, but then the next sentence is interesting. It says that R equals to minus S minus T, and why is that? So I drew it out, and after some mess up, I eventually was able to get it right. If R equals to negative S and negative T, that just means S plus T equal to negative R. So here's what the way the book wants it. Now, why doesn't it just say S plus T equal to R? I am not sure right now. And maybe anyway, so if you draw it this way, okay, then S plus T will be equal to negative R. All right, so there's our triangle. And what are we doing with this? Yeah, being that we're going to square everything, I don't think there will be much reason why R isn't S plus T, but rather this negative business. Yeah, and then of course S dot T equal to 0 because they are perpendicular. So then we'll plug everything in. So R squared, okay, that's the third side squared, which is R dot itself, which if you write it out will become, the dot product by itself. Of course, all the negative signs will cancel out. So there was no reason to pick R to be the negative, okay? That just made me waste time trying to get this triangle to come out right. Anyway, so it equals to, if you multiply this stuff out, it equals to this because the T dot S and the S dot T all end up being 0 due to this point. So then all this just S dot S and T dot T, which is conveniently S squared and T squared, just like Pythagoras theorem says. However, the next sentence is amusing because then now that we proved the Pythagoras theorem, we notice that actually to do this we have to use formula E, which says S dot T equal to 0, okay? But formula E was actually used Pythagoras theorem in its proof. So we are sort of going around in circles, but so this example isn't actually to prove the Pythagoras theorem, but just an excuse for us to practice messing with vectors, okay? So that is, that's all we are trying to achieve here. And so the next thing I need to do is example C, where a plane is cutting through some sphere. Okay, now if a plane cuts a sphere orthogonally, now that matters greatly. Don't forget, the plane is cutting the sphere orthogonally, and then we're going to prove if that is the case, then we're going to prove that if it passed through the center, if the plane passed through a sphere orthogonally, then it must pass through the center. Now that might sound familiar. That's because that's an old problem from geometry, I believe. Okay, but we're gonna prove that again now, because we're gonna prove it with the help of vectors, so that we can practice messing with vectors. Okay, doing things the vector way. And so for that, let's. But even with the vector way, we still have to draw a picture of it. Okay, here's my plane that I pretend not to pass through the center, which is B. Okay, the plane's normal is called A. And let's say the plane and the circle, the sphere, intersects at R. All right, so far so good. And then we're going to now, we're still going to borrow quite a bit of facts from geometry, okay? Otherwise, we can't get around this thing. So, but we'll use as many vectors as we can. So R is a point common to both plane and sphere, okay? And then R is right there. And then R minus B is the vector from B to R, which is perpendicular to the sphere. That just means it's perpendicular to the tangent at that point, at R of the sphere, okay? And then A, of course, is perpendicular to the plane, because A is the normal of the plane, so it always is. And then so from this to these two information, then we conclude that being that the sphere is perpendicular to the plane, that's given. It says that it's orthogonal. And by the way, the word normal means perpendicular, orthogonal means perpendicular, and perpendicular means things are at 90 degrees, right? So we got all these stuff. That being that we already know that the sphere is perpendicular to the plane, which means the tangent is perpendicular, okay, at the intersection. So then with all this perpendicular business going on, then we know that A has to be parallel to the tangent of the sphere at R. And being that R minus B is perpendicular at that point, then A is perpendicular to R minus B. Okay. Now, if you stare at this long enough, it'll all make sense. Things are perpendicular, parallel, etc. From geometry. So then, being that they're perpendicular, then we know that the dot product is 0, which we can rewrite as RA equals to BA. Which now at this point, being that R is on the plane, and so R dot A equals to K, right? And R is a point on the plane, because we said R is common to plane and sphere. So then if R dot A equals to K, well, then B dot A is also equal to K, being that they're the same. And so if B dot A equals to K, then B is also on the plane, because the plane is defined as anything that dots A equal to K, okay? And that is that's the definition, one definition of planes. That if you don't remember how that works, please review the concept. But that is, yeah. So for that is example C. Yeah, so we have come to the end of this section. As a whole, please read the entire section carefully. Okay, there's a lot of interesting tidbits, and but most of it is repeating what we knew, but what we've learned in the past. But to do this section, you have to be pretty familiar with the facts, not how they were proved, but just that they were there, okay, in order to do the homework. So please do read the whole section carefully, and look up anything you don't remember from the past. Just need your memory refreshed at what all the facts might be. All right, and of course, do all the examples yourself. Redo all of them to make sure that they make sense, and that you know how to reproduce the stuff, because you're going to need that in the homework. So for homework, page 69, please do all of them, okay, which is problems number 1 to 18. I know that seems like a lot, but a lot of them are very, very short, so they don't really count as much of a homework. And I feel that it is important to do all of them, because vectors are somewhat odd, okay? And especially if you haven't touched it since Calculus 3, it might feel unfamiliar, and doing a whole bunch of homework will get you up to speed as to how the subtraction of vectors, dot product, cross product, perpendicular, all that stuff. All right, so please go do your homework, and when you're done, I want to talk about all of them. So page 69. Let's look at problems 1. Okay, problem one is just a matter of doing some basic calculations. The area is A cross B, which becomes that. Okay, and problem 2, calculating the midpoint. The midpoint is just two vectors divided by 2. In fact, the vector be divided by 2. And in this case, the vector is r minus s. Okay, and it goes from r to s. Doesn't matter which way it goes, s to r either way. And we just divide it by 2. That will give you the midpoint. And then let me think about what I mean by that. I should be careful what I'm saying, okay? And the midpoint should be figure out which way we're drawing it. See, we're going, if the vector is pointing from r to s, with the midpoint should be s minus r, and then divided by 2. Otherwise, I mean, is it as, yeah. Yeah, let's not think too hard about midpoints. Next, let's consider some line segment from R to S, okay, with some kind of ratio. Well, we'll just do that. That is, the ratio is, let's say a ratio is from ratio k to m, okay, which is at some point x equal to 0. And we need to figure out the line segment or something. And by m is, m gave us this relationship where x minus r equals to t s minus r, where t is some number between 0 and 1. So then if we let t equal to this particular proportion, and then everything should work out. Okay, then x0 will be start at r, and then with that proportion given, and then it will get all the way to x0 like it's supposed to. Now the problem 4, we need to prove that if r s t 3 vectors on a straight line, then some kind of a line relationship had better come out. So what we're going to do is by equation m, okay, then we will figure out that first the r and s will have this equation, the line between them, okay, and then s and t has a similar relationship. Then we add up these two numbers and get up to be something like this, where we allow k equals to L1 over L2, and then we get the equation that the book is asking for. That's assuming they are on the line. Secondly, if they satisfy the equation, that is, we prove backwards, then we can just I imagine we can just do the reverse process. That is, can the reverse be done? Let me think. Yeah, the process can be reversed easily, although I probably should have written it down here. Is to reverse the process, you just let L2 equal to 1, okay, and then k equals to L1, that kind of thing. And then this whole thing will drive backwards to wherever we used to be. And then come up with this the equation up here where it shows that, again by m, that the two things are on the line, and that each of these two things are on the same line. Anyway, so yeah, that's that. Let's move on. Now, next, problem 5, we have the center of mass formula, which I've copied down online, okay? And the center of mass formula, that is for one-dimensional objects. And then 3-dimension, you just slap down vector symbols on there. Nothing's changed. Okay, so then what happens then is you calculate all 3 components of the center of mass at the same time. So that is problem 5. And next, problem 6. If you have problem 6 is to prove condition I believe. And so then if you have 3 vectors that's parallel to a plane, remember the 3 vectors might not even be in the same plane at all, okay? They don't have to be parallel to each other or anything. Then then we have the interesting situation that RST, the determinant, will become 0. Now to prove that, actually I found out to be very short. What happens is, well, being that they are parallel to the plane, so we pick two of them, then S and T must be perpendicular to the plane, right? I mean S cross T, being that S, that's the cross product, is perpendicular to its own stuff. And so then which means R is perpendicular to S cross T, and then so R dot S cross T is 0, which is RST, the determinant. Okay, that is by something on page 64, I believe. That's the one of the things we mentioned about the determinant is the dot and cross product of something. And so that's problem 6. And next, let's look at problem 7, where we have the area of what is problem 7 anyway? We're supposed to prove that distance formula between line and point. All right. So to do that, we are going to calculate. Okay, we're going to draw this thing. Okay, there's my vector r, and then my vector r and my vector s. And then together with A, which is the direction of the line, okay, we will form a parallelogram whose area, of course, is S minus R cross A, with absolute value and stuff like that. So then if we divide it by the magnitude of A, which is the base, then it will give the height of the parallelogram if A is considered the base, the height D, which then so D would be equal to the cross product, okay, divided by A, and that is the formula. So next, let's look at problem 8, where we are proving the distance from point to plane, okay, which we have done in the past, but we're going to do it again. So to do that, the book gave us extensive hints, which, okay, so we will follow those hints. And so first, T minus S is parallel to A, therefore, T minus S equals to some constant, some scalar K times A. All right, next, R minus T is perpendicular to A, so R minus T dot A equal to 0, which also means RA is equal to T, R dot A equals to T dot A. Third, the distance that we're looking for is S minus T, okay, the magnitude of S minus T, which, as we mentioned earlier, S minus T's magnitude is Ka, which is all right. And we'll assume K is positive for the moment. For the cause of this story. And anyway, so then I was lost here, okay? After that, I didn't know what to do. I did something, didn't work out, so I tried something else later. And later, then I decided to pull this trick. S minus T is equal to Ka, fine, which is the same as K times, well, multiply top and bottom by magnitude of A. So now we got A squared over A there. And so then that gives me, what's A squared? That's A dot A, okay? Then we'll plug everything back in. Well, T minus S equal to A, as we mentioned before, equal to Ka. So we plug that in here, and then split it up, becomes the two dot products. There's T dot A and then S dot A. And then I replaced T dot A with R dot A, because above, over here, we mentioned that R dot A and T dot A are the same. So I replaced it, and now we are somewhere. Now we factor it out, and that's exactly the formula we're looking for. See, way up here, that is what we're looking for, and that's what we got. So that sounds more work than it would have been if we were to do it the old-fashioned way, I'm sure. But this does help us manipulate vectors, okay, and see how that try to figure out how to get vectors to work for us. All right. So next, next problem 9, we're trying to calculate, I guess, sine theta or something. Whatever. The point is, the area A, of course, is R cross S, the magnitude thereof. Or we're trying to solve that. Well, either way, whatever it is the area of A is R cross S, which is by geometry, that's RS, the area itself is RS sine theta. Okay, so then of course sine theta is then equal to, if you get rid of all the rest of the stuff, is equal to this thing. So that's problem 9. Next, we are going to look at problem 10, where we prove law of the sines. What's the law of the sines? That's this thing right here. Okay, I have drawn a triangle on the other side, where two sides are r and s. The third side is s minus r. Okay, and the end minus the beginning. So then I label the angles ABC. And so what we're trying to prove, of course, is that sine C over R is equal to sine A over S and sine B over S minus R. So then what is sine B? We just had that calculated sine B in the previous problem when sine B equal to the cross product over the magnitude of stuff. Okay, and similarly, so I wrote it over there. And then similarly for sine A and sine C. See, and then you notice that if you divide by sine A over S, that is this equation right, where's sine A? Right here. Okay, divide by S, then it is equal to this thing, right? And that's the same as, because then the denominator has all three objects in there. It has S, R, and S minus R. And that's the same if you do it to sine B, dividing by this, and sine C of these equations that we come out, divide by R. They all equal to this equation, which means they all equal to each other. Now, isn't that neat? All right, so that's the vector proof of the law of sines. Now, next, let's look at problem 11. Problem 11 have us calculating the volume of a parallel pipette. Okay, that's the thing that looks like an eraser in the old days, but I'm not going to bother doing that. And well, what I did is I just looked up Calculus 3 book on page 178, where it gives the exact description. It gives this fact as a theorem, and the proof as well. Okay, what happens is, turns out it was quite simple. And once I realized what was going on, the base is of course s cross t. And then what's the height? The height is r dot the normal vector of s cross t. That is, let's say this is s cross t, and what I did is divide it by its magnitude, so that is a unit normal. Okay, not just normal, but unit normal. And therefore, when you take v and dot the unit normal, then it gives you the exact component in this direction. Okay, and so which means that is the height of the parallel pipette with the first two vector consider the base. So if we dot the third vector, which is well, whatever, and once we dot it, that produces the height. Okay, and then so the volume then is equal to the height times the base. And then you notice that the denominator conveniently cancels itself. It becomes r dot s cross t, which is by definition on page 64, RST. All right, that's the determinant, and that's how we calculate. And so that came out very nicely. So next, problem 12. Now, I had no idea how to do problem 12. There was so many stuff, R, S, T, U, V, W, are you kidding me? And then I was confused as to what the book wants. So eventually I looked at the answer. Okay, and once I looked at the answer, then I realized what I'm looking for. So here's what I did. So here's the mess, the stuff I messed around and got nowhere. And then eventually I decided that we'll use the triple scalar product, or whatever this is called. Okay, we'll take the first item and dot the cross product of the other two items, which is fine. And then we apply Lagrange's identity on page 64, which if you apply it very carefully, with the cross product stays the same. Okay, on the second side. So you only break up the first cross product, which equals to this thing. And then when you look at this thing carefully, that is just RTU, okay, in a determinant form, and SVW, and so on, equals to this thing, which is the correct answer. And I guess that's all the book wants us to do, is to change it into a bunch of determinants. Well, I think they should have just said that, prove that this equals to that. That way we know what we're shooting for. But still, that is a pretty neat use of the Lagrange identity, so I'm happy with it. Next, let's problem 13. Let's prove something from geometry back in the day. Okay, we have a line that goes through R in the direction of something, and we need to set t equals to 2/3. And then something interesting will happen. So we are going to prove the median, and by using the equation, what is that? Proposition M on page 67. All right, we let which says that the line is x minus r equals to t a minus r, where a minus r is the direction of our line. So then, if we let t equals to 2/3, and so we'll solve for x in this equation. So soon we come up with something, and we solve for x and let t equal to 2/3 in this equation. So after some algebra, we end up with this, okay? That x that is equal, the point that we're looking for is at 1/3 r plus s plus t. Now that answer will be the same even if we were to go through r or s or t, because it'll end up being symmetrical, right? So if we were to change the name to s or t, it all end up to be the same point. Therefore, there's the 3 points that the median intersect, all three medians intersect at the same point, which is 1/3 r plus s plus t. So that's that. And the next, let's look at problem 14, the centroid. The centroid is the intersection of medians, okay? All right, which by the previous problem is the 1/3 of r plus s plus t. And then as a result, then we have a bunch of subtractions that we are supposed to prove. Then if we add up r minus u and s minus u and t minus u, then would just be be minus 3u, which is just r plus s plus t, so then it equals to 0, like it wants to. All right, next let's consider problem 15. Problem 15, I at first had trouble again making things come out because, well, problem 15, of course, is some quick problem from basic geometry. But to prove it with vectors, there's so many lines, and which one am I supposed to consider? Okay, so I couldn't get it to go, and I was making a big mess there and got nowhere. And so I looked online, which didn't really help. And there is actually, eventually, I was able to find this one website that tells me how to do it. And then, but when I read through it, I realized it was wrong. It is too funny. But however, even though it was wrong, it gave me enough ideas that I was able to get to the end. So it was still helpful, okay? And so then, so here it is, which once I found out the idea, then actually the solution is rather simple. So the idea is this. We are going to, I draw the whole thing out. Now I'm going to use this different notation to, because there are so many points, okay? So this I feel is clearer. But the point is MQ, where's MQ? Yeah, MQ is connecting the midpoint that is from AB and BC, okay? And what matters here is we will know that MQ, the length of MQ is half, in fact MQ itself, the vector, is half of the vector of AC. Okay, if you're allowed to move vectors around, because that's because the triangle is the midpoint and so on. Okay, the stuff joining the midpoint is half the stuff at the base. This is from geometry, and we're going to use that information. So anyway, MQ is half of AC, and we'll call AC R for the math later. And then similarly, QN is half of BD. All right, in the same direction. So that is equal. We'll call that S. That is, we'll call BDS. So then MN is which I didn't draw here, which is equal to from vector notation is equal to MQ plus QN. All right, it goes from MQ and then ended at QN. Right, so that equals to each one of these, as we mentioned, is half of the other stuff, which is when you do the math, is 1/4 of r plus s squared. Now next we consider QP, a similar situation. QP is actually equal to QN, and and Qn and then plus NP, right? But NP is negative of MQ because things are parallel and they're both half of AC and so on. So anyway, so it becomes minus MQ in that direction, which means in terms of vectors, is similar to this one is equal to this thing subtracted by that, because Qn is BD, etc. Okay, so that's the interesting point where we use vectors in this case. So once we do that, then which then equals to quarter of R minus S. So you notice these two things, one is R plus S and one is R minus S. So then, well, by the time we do the vector algebra, okay, what are the magnitude squared? That's the dot product. So we'll take the first one, we'll take R plus S dot R plus S, okay, which the dot product give us this thing. The second one will take R minus S dot R minus S. I have it written down here. Okay, that the top one is R plus S dot itself. The second one is R minus S dot itself, which will become the magnitude squared respectively, and then we'll add them together, and you notice the middle dot products disappear, and we end up with just the end and equals to half of this stuff. That is the MN and the QPs all squared together is half of the diagonal squared added together, which is what we are trying to prove. So that is so with some bit of luck, I was able to get to the end of this problem. Otherwise, it was it was confusing as to what vector am I supposed to use. There are a ton of lines, you know. I didn't even, you see in the graph, I didn't even connect the midpoint, because there'd be so many lines that we're talking about. See, we're talking about MN and PQ. But once you notice the direction that we should attack this with, which is basically this. Okay, this is the knife that we're going to stab it with right here. Once we realize this, then everything falls out very nicely. So that's that. And that's problem 15. Next. So next, let's do problem 16. Well, they should have said problem 16 first. Okay, I mean, since by problem 16 we already know this, and because we know this from problem 15, the MQ is parallel to AC because it's midpoint and stuff like that, and then PN is also parallel to AC, okay, because it's the midpoint and stuff, so it's parallel to the base. It's from geometry somewhere. And similarly, the other two sides are also parallel, and therefore that thing connecting the midpoints is a parallelogram. That's all there is to say to it. And problem 17 is also a quick walk in the park. We're proving area of a triangle, and which is the parallelogram. Area of a triangle is parallelogram divided by half. So we have that is equal to the cross product divided by half, and which is half of AB sine theta, and then A sine theta is the height. Okay, and as I draw in a little graph here. So then base times height then over 2 is the area of the triangle. All right, so that's that. So finally, we have come to problem 18, the last one. Problem 18 is just a matter of writing things out and noticing what's canceling what, because we have a lot of symbols. And not mess up on the symbols, okay? Remembering what are we subtracting. So we have 3 vectors. Let's start with just a polygon of 4. And so we got 4 points. And we have 4 points, then what are we doing? Let's see. Okay, we have the vectors. First, we'll define the vectors. Okay, we have the points, which is x1, x2, etc., y1, y2. And the vectors, the first vector, we'll call it v2, which goes from x2 minus x1, y2 minus y1. And we'll do it in 3 dimensions. And of course, the third vector then is 0, because this thing is only in 2D. But we'll extend it to 3D so that we can do the cross product. So now that we have defined our vectors, then the first area of the first triangle, okay, this one here, I wrote down A2, will be equal to V2 cross V3 as we defined there, and of course divide by half. So then I calculate the cross product, and and quickly, then you come out, and then only the k coordinate remains. Then being that we're doing the magnitude, we can ignore the k. And so then we have this stuff, okay? It has x. And you notice that in this equation, the x1, y1 cancels itself out. So then we have 3 pairs of things, okay? This one, that one, and the third one. Now, then the next thing is we need to write down the A3, so the area for the next rectangle. Let's see. And when you write that down, we have, well, at first I got confused. But anyway, but you can follow the same pattern as long as you're doing the right pattern. Remember, everything goes back to subtracting. You have to subtract by x1, y1. Okay, we all go back to the same deal. So then, so A3, at first I messed up and forgot that we're subtracting x1, y1. But by the time I got remember that, then we end up with A3 equals to this thing. And you notice that this part that I marked as beta 3, okay, is identical to the beta 2 in the A2, except with a different sign or something like that. In such a way that, see, they're different signs. So then they cancel each other when you add them up. So then each term cancels out one term with a future triangle and one term with a previous triangle. So each area ends up with just one term. Okay, so we'll add them all up, and that would be equal to the first one. See, the first one is what stays, because the next one, it gets canceled out in the past, and then the following one get canceled out in the future. So all we have is the first term left, this thing right here, which which will, and don't forget the 1/2, right? And then which by the time we look at it, that is the same as the determinant as the book wants, and that is the end of the proof, and that's the end of this section.